So I've been working on the epi modeling of community-based Sentinel surveillance approaches for pathogen-agnostic early detection. Couple caveats being most of my time has been spent learning Python from scratch, epi modeling from scratch, and biology from scratch. So I've only been able to start generating the kind of final batch of results literally today. Hopefully they'll be ready by tomorrow. And so you'll get to see everything in the write-up. But I'm going to spend more time going into the actual methodology for this reason. And Isabel also gave a great overview of why metagenomics. So I'm not going to go too much into that either. Briefly going over the outline and motivation. So it seems like pathogen-agnostic early detection is a good thing. And where we are right now is that we're beginning to see proposals floating around, such as ThreatNet, such as using donated blood screenings, such as leveraging private diagnostics, and no real sense of how to compare these, as well as answer some of the basic questions that policymakers and philanthropy organizations really want to know in order to be able to put money towards actually building something. So you can see some of those questions on my screen. And I wanted to focus on community-based sentinel surveillance because on priors, it looks like we're going to face less issues with adoption than syndromic surveillance. It'd be hard, for example, to get the NHS to learn how to do this thing and train loads of lab workers, as Isabel mentioned. And also there are fewer bioinformatic challenges and wastewater sequencing. So in order to think about the cost effectiveness of community-based sentinel surveillance, I began looking at how we can answer the questions that you see on your screen. So these are actually built the thing. The standard in epi modeling, as Isabel explained, is an SEIR model. So ultimately you have 4 compartments and you're tracking the numbers of people in these compartments as they evolve over time. And that gives you the distribution. So that distribution effectively tells you what's going on, allows you to model pandemic spread. And in particular, what you're doing is for each compartment, you have a set of differential equations that tells you how these things are changing. An agent-based model works a similar way, but rather than tracking compartments, you're tracking each individual agent where every single person is able to go through some of those phase changes. But you're also, through some mechanism, finding a way to simulate the contacts and relationships that each agent have. So you can group people into certain households or workplaces where they have a much higher likelihood of coming into contact with this person. In other words, a much higher likelihood of their overall likelihood of transition to the next phase change being shaped by one subset of people as opposed to another subset of people. And this allows you to start modeling all sorts of heterogeneities. So the model I was using was, first of all, CovaSim is an open source model that you can find online, which is really cool. And the team at McGill University have been building on top of this, called PathoSim, where they've built some additional functionality with respect to multi-agent stuff, primarily. And this is the basic phase change that each agent is going through. But the most important thing to understand about how this works are the next 2 slides. So the way in which, well, you might be thinking, it seems like you want to replace 4 compartments with 20,000 agents. Isn't this just like extremely intense and like hard and difficult to do and computation expensive? The trick is that rather than a big lookup table of every single agent and their attributes, you just have a bunch of distinct arrays which are storing lots and lots of numbers that aren't necessarily talking to each other, but the index position of every single attribute in the array corresponds to a single person. And you just ensure that as you're doing the calculations between every single of those arrays, you're making that property the same. This is the central thing that allows you to model both infections and the things that I'm doing. So just as a quick example, what this actually looks like is, let's say you just have an array of just like a number of agent contacts per time step. What you do is you apply to every single number some transformation algorithm. So this could be something that creates a probability. Then that probability creates like a Bernoulli trial. Then that creates like a random generator. It could be anything you want that generates the array of viral loads. You then have a filter where you randomly test people. Again, you don't necessarily need to, you just like have a long list of arrays, just like, okay, this many people, false, then true, then true. That's what testing looks like. And then what you generate in the final array is the detections. So let's say a viral load of above 3. In this case, this is log copies per milliliter. And then you only return the results when the agent selected is also true. And this way we've gone from an array of unspecified indices to like an actual detection that follows a logical procedure without necessarily having some big table holding everyone's information. And this is ultimately the trick that I'm pulling to model this over and over again. So I'm thinking about returning the viral loads of a subset of the population at every single time step to model Sentinel surveillance. So I base it off the following stratification like techniques which seem promising to base on. So one, just random testing, but also trying to select people based on the probability of becoming symptomatic, which might proxy things like people being in precarious environments like near a reservoir. But proxying by people based on how much contact they had, you might want to populate sample a population like people in airports because they have so much more contact, much likely to come into contact. Age-based stratification is also just already in the model, so it's easy to do, but people who are elderly are more likely to kind of express a higher viral load to begin with. And then I also built a syndromic pipeline as well. And for the actual sequencing, once I return those viral loads, I'm plugging them into effectively simulation data that I've already had, which is generating a number of unknown reads. And this is broadly quite similar to the kind of detection procedure that you might expect in the real world. Just like how many things do you see that are totally unknown? And I can do this and account for pooling. So between both of those things, I'm able to account for various heterogeneities that whilst this creates a bunch of challenges and is totally unnecessary to model the vast majority of things, where an SEIR model just does super well, I'm able to account for things like different amounts of pooling and different kind of population setups and testing, different filtration procedures, different rates of people going to the hospital, and so on. So with this, I then parameterize this by actually replicating ThreatNet, or at least attempting to. And yeah, ThreatNet, you basically have an overview of what this is doing from Isabel. So I can skip this. But yeah, so these are the results in the original ThreatNet paper based on the US that I wanted to replicate, where I specifically focus on replicating the 30% coverage. And I'm not going to go into details of my replication. It was super rough. I'm going to go back and do it. There were a couple of assumptions that I had to make because I didn't have data at the time that I now do have. But I'm effectively able to replicate the time to detection, and I get like a total cost that's not like kind of ridiculous. So the results will be like imprecise but directionally correct. In particular, here's my replication of the basic infection progression. And here's the actual results. So you can see that the number of days are pretty ballpark, not too bad. The number of infections based on are higher, but it's actually unclear that sensitivity will have like a massive effect on the number of days if you think about how syndromic surveillance is working, but this is something I'm going to go over and check. So now I'm going to spend the last couple of minutes discussing the kind of results that I do have. So the first thing is I focused on answering the questions by designing studies for each of them. So Sentinel surveillance versus ThreatNet, where Sentinel surveillance initially just random. Then thinking about what kind of the different types of stratifications I mentioned, which one is the kind of most exciting. Then what's the actual sequencing regime? So in particular, depth, i.e. the number of reads you're actually doing. How does this affect packaging characteristics? And then taking all this into account to try and propose what's a really good regime. But noticing I basically only have concrete data for the first. The data I do have for the first is I ran 600 simulations of a random population Sentinel surveillance where I varied the percentage coverage of the population and how often. So these people are being tested. So every single day, once per week, once every 2 weeks, and effectively once per month. And I got a pretty exciting result. I'm going to spend a lot more time double checking. But with 0.2% of the population, which is still quite a large number, but being sampled once per week, roughly matched 30% coverage, yet came in much cheaper. I should say this figure for how much it costs is the variable cost of sequencing, doesn't account for the actual operational cost of receiving this many samples per week. So this is something that I just need to independently estimate. And there are some reasons it might not generalize well. So for syndromic surveillance, it's fairly straightforward to treat this setup I have as one hospital and just multiply by the number of hospitals. It's unclear that logic generalizes to what I'm doing here. But it does reflect the fact that much fewer runs are happening with Sentinel surveillance, because you're able to select a smaller proportion of the population than would be syndromically appearing, at least past a certain point, and also much higher sampling pooling sizes than even I've actually accounted for here. So at the very least, this is like ballpark, extremely low confidence estimate. Like, there could be something super exciting here that I want to spend next month thinking about a lot more. Similarly, it seems like there's a really strong effect of testing every single day, such that a much smaller proportion of the population being tested regularly was even cheaper. And this might be kind of exciting to explore more. Now, I don't have any data for ideal Sentinel surveillance, but in my own internal trials, something that is interesting is that I just basically don't know, but severity-based testing, i.e. testing people based on this probability of becoming symptomatic, just seems to do really, really well. This is kind of intuitive, and this means I want to kind of think more about, okay, who are actually the kinds of people that we know are likely to be symptomatic early, but I think this looks like people who live near potential sources of conflict, as well as people who are maybe in potential sites of like a terrorist attack. So this is worth something thinking about. Similarly, ideal sequencing regime is not something I currently have data on. That's being run. Again, all the simulations are just like in the middle of being run as we speak, as you can see here. But what I will say is everything I've done so far has assumed quite a low depth. So I'm only doing 10 million reads, whereas something like the MySet can do 25 million. And I haven't even thought about modeling very high throughput sequences that can multiplex loads and loads of samples of people, as you might want to do with a Sentinel program. And this could be a very big cost lever. And I basically have not much on pathogen characteristics other than I think what Isabel has already mentioned, which is, although I should say, from what I have tested so far, syndromic surveillance is like much more sensitive to incubation period than all the others, which is kind of to be expected. But I think is an interesting result for thinking about both biosafety and also like like terror. So yeah, basically my next steps are just to fix the model and replicate net, improve the studies, rerun those simulations, and then hopefully produce a white paper where integrating my architecture into pathogen to just generally boost the world's epi capabilities, publishing a paper and reaching out to stakeholders, and continue developing pathogens capabilities. So hopefully how we get one step closer to pathogen diagnostic early detection.